All right, for lab number, what number is this? 47. Falstad does not have a voltage regulator, but you can make one. And because it uses some formulas, it has some fallacies, and I'm going to introduce you to them. But I want you to see what a voltage regulator does. Now, on the LM317, we have an adjustment. That's going to be this pot, and we adjust it over here. And this is our feed voltage. Now, because of the way this thing calculates, we will actually be able to get out greater than what we put in, which really can't happen. And this is our output. So input, output, and adjustment, which is our variable resistor here. So you can see here I've got 35 volts coming in, and I'm going to adjust it to get 12 volts out. So I'm going to move this until we'll call that 12 volts. So the nice thing about a voltage regulator is even if the load changes, and I'm going to come in here and change that to 100K. Actually, I should have started with 100K, which isn't much of a load, and you see it's still 12 volts. And if I change it back to even a 10 ohm, which is a pretty good load, we're still at 12 volts. So the nice thing about a voltage regulator is it does hold the voltage at whatever value you dial it to, regardless of load. And that's the beauty of a voltage regulator. Now you can see I crank this thing all the way up. It goes 249 volts. That's not possible. But the unique thing about it is they will bottom out not at 0 volts, but around 1.2, 1.3. And that's pretty common. And so you can't really get 0 volts per se. So the nice thing about this is it is used for voltage regulation. So I'm going to kind of go through your questions for you just to kind of give you a feel. And the very first thing it's doing is it says set VN to 35 volts, just R2 between its two extremes, and that's what we were doing. So your bottom is going to be around 1.2, but your top should only be about 29.2. So that should be your two ranges there. So again, the fallacy of this simulator versus the real world. In this case, simulator is pretty good otherwise. And then it says adjust R2 for a 12 volt output, and we did that. So let me go back and redo that again. 9, 10, whoops, right by it. Get closer. There we go. Close enough. And it says without disturbing the setting of R2, look at the V out here, and so what you should see is on step 4 is let me reread that. Without disturbing the setting, record the output voltage from the regulator for a value of 15 in and 25 in. Okay, I see what it's asking. So we got 12 there. So we're going to change that to 15. And notice it's still 12 volts. So as long as we're higher, it's going to produce that value. And then it says go back to 25. So 25. So still 12 volts. So that's what you're expecting to see. And step 5 is your line regulation. And what it's asking for is the V out over the V in. And let's see where it asks you to get that from. Use the results step 4 and calculate the line regulation of the circuit shown on. Record your answer below. So V out over V in. Trying to figure out where they're getting these values from. It's coming up with 12 millivolts over. Oh, I see what the difference is. So, okay, let's back up. I don't want to show you all the answers. Well, actually, it won't matter on this particular one. But what you'll find out, because I am pretty much giving you the answers, is with an LM317 there, it would be 1.25 to about 29.2 with 35 in. Now, swapping those voltages, we're getting 11.96 versus 11.988. So there was only 12 millivolts difference there with a 10 volts difference in the voltages feeding at 15 volts versus 25. So that 12 millivolts per 10 millivolts is 1.2 millivolt per volt of discrepancy, which is very little change, is all that's trying to point out. So there's all the answers. I'm not going to make you build this circuit because it was fairly complex and there's some parameters, but just know it's there, and it acts just like the LM317 other than the higher than output. Now I want to talk about, I'm not making you do part two, and but I wanted you to see this. This is a standard AC input transformer, and we're getting step down AC 25.2 volts, and we're running it through a bridge. And of course, a bridge just takes and doubles our frequency and smooths out our waveform with the capacitors here that you see. And I'm going to attempt to draw that. Y'all, if you've watched, know I'm not an expert drawer when it comes to this stuff. But without these filter caps right here, what basically happens with this is, we've got a sine wave. Whoops, let's use a different color. And let me find where my pen is. Here we go. So let's use pink. That'll look jolly good. So our sine wave here is looks like this, and of course coming out of the step down, it's going to be a much smaller sine wave. It's not going to have the same amplitude, and again, that's supposed to be a perfect sine wave. I understand that's not. But what this bridge rectifier does is we get rid of the negative cycle and we flip it positive. So you got a sine wave out here that looks like this. So and this is the line. So what we're doing is we're flipping this bottom half, so the output waveform looks like this. So we double, and those are supposed to be even, and they hardly are. Let me try that one more time. So we double the frequency. That's a little more even. It's not perfect, but you get the idea. Basically, we're taking this guy down here and flipping him positive, like that. And that's where we get that. So then these filter caps, because what you've got before is you've got alternating current. You had something that looked like this right here. There was a distinct rise and fall. Well, by bringing it up, we made it look a little more DC-like, because this is going to repeat over and over and over again. So what you end up with is something that kind of is a steady on, but we've still got these valleys here. But when we put in these filter caps right here, that comes to look more like this right here. It gets away from those negative peaks. So we have this sawtooth looking wave, but it's mostly a positive DC. And the reason it's DC is there's no longer any negative down here. And so we can take that and we can bring it in, and it's going to be a fixed value based on this bridge. And when it comes in, this kind of sawtooth waveform, it's going to pretty well see that as a DC. We can adjust, and we can get a nice fixed DC source out of this output right here, regardless of the load. And so that's why these LM317s are so nice. If you want to make a variable DC power supply, not very many components involved. Step down transformer, bridge rectifier, a couple of filter caps, an LM317, some more resistors and caps, potentiometer, and you got yourself a bargain basement dirt cheap power supply, DC power supply here. So these are pretty neat. This is the kind of thing that you can build. You can find these kits online, or you can take the schematic right here, go to your Amazon, your eBay shop, and order those parts and take and build this thing and have you a working DC power supply and with very little investment. So just wanted to show you that, and that's why we like these 317s so much. So anyway, I hope that clears up some of what this was all about. And again, you get out of the lab free, but I did want you to see, and you're going to have to at least listen to me to get those answers. So there you are.